Okay, section 4.2. So in 4.1, we introduced integrals and antiderivatives, and we said that we were shifting the class from what was differential calculus into the start of integral calculus. And the primary thing that integral calculus is concerned with is areas. So we're going to be looking at antiderivatives as areas in this section, and we have two things to talk about. The first is area under a curve. And the second is approximating areas and this is Riemann sums. So as I said, integral calculus is primarily concerned with area below a function, specifically the area between a graph of a function and the x-axis, because that's positive area. And usually when you're looking at area, for our purposes, if you're thinking about cost or population, you want your cost or your population or your revenue to look at the positive, not the negative. Cost might be a bad example there because maybe you do want negative cost because it means you're earning money. But anyway, there's a lot of situations where we can interpret area in a very important way or a meaningful way. And at least in this section in 4.2, we're going to be assuming, and this is important, that f of x is strictly 0 or greater for all of our functions. So we're going to look at a few examples and a few different ways to talk about it. So in this first one, we're going to be looking at business and total cost. So Covington Bakers determines that the cost in cents per pound of its sourdough bread is this function c of x equals negative 0.2x plus 125 when x is less than 500. And x is the number of pounds. We're going to find the total cost of baking 140 pounds of bread. And we're just going to disregard fixed costs to make this a little bit easier. So for this particular problem, we have a nice linear function, which means that we can break our area here, the shaded yellow region, into two pieces. And we're going to do that here at the 100 mark. Because the 100 mark is the straight line, if I could draw straight lines across. And we're going to think of this as A1 and this big part as A2. So this is the cost. So all of this area represents our total cost. And so our total area is A1 plus A2. Now, why would we want to split this? Well, this is a rectangle and this is a triangle. And we know the areas of rectangles and triangles very well. So the area of a triangle is 1/2 base times height. So the height is 25, 100 to 125. And the base is 0 to 140 is 140 divided by 2 plus base times height, 100 times 140. And we can calculate that out, and when we punch that into a calculator, we get 15,750. Since this is cost, this is in dollars, and this is total cost. So that's how much it will cost the bakery, ignoring fixed costs, for baking 140 pounds of bread. So this is great. When you can split your region into geometric shapes that we know the area of, rectangles, triangles, squares, trapezoids to a certain extent, if you know, but you can split your trapezoid into more triangles and rectangles. That's what we're looking for to do, is because that's easy and we understand the area of those shapes very well. And by very well, I mean they have a known area formula. So let's look at an example that we can't do that on. So here we have this company is its marginal cost in dollars when X suits are manufactured is C prime of X equals 0.0008X squared minus 0.45X plus 100. Again, we're going to ignore fixed costs, and we're going to approximate the total cost of producing 400 suits by using 4 rectangles. So I've already gone ahead and done this for us. And we're just going to ignore this for a second and talk about why we want to do this. There's no good geometric shape that you can make out of this curve. So if you were to try and split this, let's say at the 40 mark here, You could split that. That is the bottom. I just, again, bad at drawing straight lines. This is still curved and this is still curved. And so we can't get a nice known area formula for anything that has a curve. I mean, we know we can do area of an ellipse, an area of a circle, but then we'd have to figure out what the eccentricity of this ellipse is. We would have to figure out how much of it we need. Is it perfectly 1/2? Is it 1/3? Is it 1/4? Is it 1/16? Make a rectangle, subtract away that piece. It's a lot of work. And so it doesn't get done. So what we do instead is we create rectangles. So let me dash this in for you. So this is the same parabola. And it's the same area, 2, 400. And what I've done is created 4 rectangles. Again, we know the area of the rectangle. So this is rectangle 1, rectangle 2, rectangle 3, and rectangle 4. So this is always going to be an approximation. So we started to see this a little bit in the end of last section where we were approximating the population of Arizona. And remember I said that your approximation isn't as good depending on your initial condition. This is the same premise. We're going to pick 4 rectangles from 0 to 400 because they break nicely into increments of 100. And we can figure out what the area of each of these rectangles is. So if we add up our total area, area of 1 plus area of 2 plus area of rectangle 3 plus area of rectangle 4, we have our total area, which will approximate the area under the curve. So this is, since this is the function c prime of x, the way that we figure this out is we know our base of each of these rectangles is 100. We picked that for a very specific reason. So this is 100, and then the height of this rectangle is 100. But we don't want to think about that as 100. What we want to do is this lies on all of these points here on c prime of x. And in fact, this 100 is actually the value of c prime of 0. And the reason we do that is because the more complicated the function is, we don't have to try and guess, if it's in between 2 integers. Is it 1/3? Is it 2/3? Is it 1/4? Is it 7/8? We just say, okay, it's going to be whatever the value is when we plug this number into this function because it lies on this function. For area of 2, again, the base is 100. The height is whatever the height is of c prime when we plug in 100, because that's 100 there. Same thing for area of rectangle 3. It's 100 times c prime of 200 this time. And then 100 for area 4 times c prime of 300. Now, if you had to take a guess just to yourselves right now, this is an approximation. Would you guess that this area is going to be an overestimate or an underestimate? So take a second and think about that. Okay, so whatever you think it is, let's find out. So if we add all this up, this is 100 times 100 plus 100 times 63 plus 100 times 42 plus 100 times 37, and all of this comes out to be 24,200, and this is in dollars, and this would be our total cost. Now, I asked you to try and guess whether you thought this was an overestimate or underestimate. And the way that this is going to work is this is going to be an overestimate. And you may have, if you guessed overestimate, you may have thought of this. It's because our rectangle is accounting for, or our rectangles are accounting for this area that I'm coloring in here. All of this area that I've just colored in is not under the curve. So it's not actually our cost. Now we do have a little bit of excess here in that rectangle, Maybe that's equal to this, but probably not exactly. But we certainly have too much here and too much here. So when you're creating these rectangles, that's what we want to be thinking about is, do I have a lot of excess? And if I do, then this is probably going to be an overestimate. There's too much area that we had in our rectangles that wasn't actually under the curve. And if we had a lot of blank space under the curve, like this one, and let's say all of these were blank underneath, then we would have an underestimate. Now, these rectangles that we're constructing, they're called Riemann rectangles, and the construction of them is what's called Riemann sums. So in that example, we use the area to do the 400 suits, or to approximate the cost of the 400 suits. So now we want to think about, since it was an overestimate, how do we make that better? How do we make it more exact? And this is where Riemann sums come into play. Technically that was a Riemann sum, but it was a very small Riemann sum. So we have a diagram here that we're going to be talking about labeling. So in this figure, a to b is divided into 4 subintervals, and when you divide your 4 subintervals, the width is always going to be the change in x. So that's this width here that I have labeled. It's delta x. Delta x is always equal to this. So we get that straight from here. We want 4 subintervals. So that means that we're dividing by 4. And it's going to make our rectangles equal the entire time. So that 4, again, comes from the 4 subintervals. It means 4 rectangles. B minus A, this is B, and this is A and this is B. So A is always where we start, B is always where we finish. So that's where that comes from. And so you can think of, if you're given, let's say we're just told find this area under the curve from A to B, your delta x, you don't even have a choice, you always make it B minus A divided by the number of rectangles you want. So this told us A to B, 4 subintervals. This is the n. So we always do B minus A over n. That's how you construct the intervals. Then your height, you'll notice each of these, the height starts at a point that lies on the function. Again, that's not a mistake. That we do this by choice. That means that all 4 heights for this first rectangle, for 1, the height is f of x1, because that's what this value is. The height for rectangle 2 is f of x2, because that's where this lies. For rectangle 3, it's f of x3, and for rectangle 4, it's f of x4. And again, we do that just as we saw in the last part, so that it's a nice, easy way to make sure all of our intervals are uniform. And then our summation takes the height times the base, height times the base, height times the base, height times the base, over and over and over again, because we know the area of a rectangle. Now, we're not always going to have just 4 rectangles. Sometimes we have a lot. Sometimes we have an infinite amount. So we're going to denote this using sigma notation. So that uses the Greek capital sigma. So our area under a curve can be approximated by the sum from k equals 0 to n of f of x sub k times delta x on A to B. So this says we take n subintervals, it's the same n. We split up our A to B the same way, making delta x, so delta x equals B minus A over n. And we take the f of xk, however many subintervals, they're integers, and that's how many points we're going to calculate. Now, before we start doing Riemann sums, we're going to do just a couple examples here working with sigma notation. And that's just to get used to how it works a little bit. So in this first one, express the sum So the way you read these is the big capital sigma says the sum. This is the sum from I equals 1 to 4 of 3 to the I. So we read it just like that, the sum from I equals 1 to 4 of 3 to the I. So this is just a big addition problem. So we start at I equals 1, we have 3 to the first. Then we tick up 1, plus 3 squared. Then we tick up 1, plus 3 cubed. Then we tick up 1, plus 3 to the fourth. Now we've hit our n value here. So that's the end. That's the end of the ticking. So then you would just add these up, and whatever that equals. 3 plus 9 plus 27 plus 81. What that equals is not necessarily important. You can do that, but the important part is knowing how to expand this. So now we're going to make this a little bit more difficult. We're going to express the sum from I equals 1 to 30 of h of x sub I times delta x without summation notation. Now this is to show you why we use summation notation. We have 30 multiplications to add up. So this would be h of x sub 1, it's x sub I, times delta x, plus h of x sub 2 times delta x, plus h of x sub 3 times delta x. And I really don't want to have to write all of these, so we're going to do an ellipses here, ellipses, and we're going to start adding then our second last h of x sub 29 times delta x, plus h of x sub 30 times delta x. So now we have our whole sum. I don't want to write 30 things. This is why we use sigma notation, because it makes it a whole lot easier to represent large things as a nice compact form. So this is expanding. Let's try transforming into summation notation. So these examples here, assume we can pretend that these are Riemann sums that we've already calculated. And now what we want to do is find the pattern. So unless you're told otherwise, it's a good idea to assume you start with I equals 1. So this one here is I equals 1. This is I equals 2. This is I equals 3, and so on. And so we want to try and find a pattern. We're going to set I equal to 1. There are 5 numbers here, so this will go up to 5. And what you may have seen correctly is 2 is 1 times 2, 4 is 2 times 2, 6 is 3 times 2. So this will be 2 times I. And this is our summation notation. So it's always about finding the right pattern. Now sometimes the patterns are easier than others. So this is a general Riemann sum here. And so what we want to be keying in on is how many terms there are. So this is x1, x2, all the way to x19. So again, unless we're told otherwise, this one especially starts at 1, and it goes all the way up to 19. So it's the sum from I equals 1 to 19. And then since we don't have any numbers like we did here, we're not really looking for a pattern. We're just writing the general version, which is g of x sub I times delta x. And that's how we collapse into Riemann sums. Now when we start finding areas in a second here, this is where we're going to start, and we want to work it into this version to get an actual numerical answer. So let's talk about approximations of area and why we choose rectangles. So I've stolen this out of our book because it's a really great diagram. Now I know on the camera it looks a little crazy here. There's a lot of little rectangles, but hopefully you have this pulled up on your computer. If you don't, you should. Or you have it printed out. That would be the best point. But so here we have 8 subintervals. Here we have 24 subintervals. And so we're going to compare the two. It's the same function that we just looked at as the example with 4 subintervals. But what you can see is here we are missing some here, and we are over on some of these. So right off the bat, these are missing area. This is too much area. And again here, this is missing area again. So we know that this isn't going to be a perfect approximation because we've got some issues. If we move to 24 subintervals, I can't really zoom in anymore in this. I think even if I lift the paper, it doesn't get any better. No, not really. That wasn't worth it at all. So hopefully you have the paper, but what you'll notice is we're missing a lot less when we increase the intervals. There's very few, and we're also in excess a lot less than what we were. So this is now the excess, and this is the amount that we're missing here. And then over here, there's a little bit missing here, 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 and there's a tiny bit over above there. But you can see that the amount that we're missing and the amount that we're going over is smaller. So we're missing less, and we're counting less excess or less extra. And so the idea is the more subintervals you create, the more rectangles you create. We had 4 in the initial version of this on the last page. Here we have 8. Here we have 24. The more accurate you get. And the width and the construction, the width and the height doesn't change. The width is still always delta x. Delta x is always b minus a over n. And our height is always f of xi. We always pick those. So we don't have to worry too much about getting that. But the big thing here is the more subintervals you have, the more accurate you are. So let's go ahead and let's construct our own here on the next page and do a couple examples. So consider the graph f of x, 600x minus x squared from a to b, or over the interval 0 to 600. So this 0 to 600, this is our a to b. So delta x, which is b minus a over n, always 600 minus 0, and we want 6 subintervals. So this is going to be divided by 6, so this equals 100. And I have the graph here, so you can see that already, but we're going to do the calculations as if we didn't. We have 100, and we have another 100, and then we have another 100, and so on and so forth. So when you start making these, you start with a, xi, or x1 is always a. And so this one starts from 0 to 100. And then you just start looking. X sub I is this point. It's always the left. That's 0. F of x sub I is the point when we plug it in. That's 0. And so f of x sub I times delta x, which is 100, times 0, is 0. That's the area of rectangle 1. This is rectangle 2, 3, 4, 5, and 6. So the next interval is 100 to 200. X sub I is 100. F of x sub I is f of 100, which is 50,000. You can plug it in or you can use the graph. And then 50,000 times delta x, which is 100, is 5 million. And then we do this for every rectangle we have. Starting, and you know you've done it right. You should always start, x sub 1 should be a. For us, that's 0. And you just add delta x's, and your final one, your whatever your nth one is, in this case our 6th rectangle, should start or should end at b. So we have 2. Let's do the next 4. So the next one would be 200 to 300. Then 300 to 400. Then 400 to 500. and 500 to 600. 1, 2, 3, 4, 5, 6, and this is B. That right there is A. That's how you know you've constructed your intervals correctly. You should start at A and you should end at B. If you start at A and you don't end at B, you need to recheck your delta x. And all this is adding delta x. So 0, add 100. Next one starts at 100, add 100. Next one starts at 200, add 100. And you just do this over and over until you hit the desired number of intervals and you hit your B. And they have to coincide. So filling out the rest of our chart here, for 200 to 300, our x sub I, that's this rectangle here, it's rectangle 3. That's at x equals 200. Then plugging 200 into F, or using the graph, this is 80,000. And then times 100 times delta x is 8 million. For the next, this is rectangle 4 now, 300 to 400. Our x sub I is 300. Plugging that in or using the graph, that's 90,000. Times 100 is 9 million. Four to 500, this is rectangle number 5. That starts at x equals 400. 400 plugging into F or using the graph, this is 80,000 again. Times by delta x 100 is 8 million. And then 500 to 600 is rectangle 6. Our x value is 500. 500 plugging into the function or using the graph, we get 50,000 again. Times by 100 times by delta x is 5 million. And then the sum, the reason we've done this is because our summation is just adding this plus this plus this plus this plus this plus this. You just add them all the way up. So it's like one big addition problem here. And the answer is 35 million. And this is approximately our area. So that's how we do it. So let's try with 12 subintervals instead. So our delta x, it's the same information, so it's still 0 to 600, only now we're doing 12 instead. So it's 600 minus 0 over 12 now. And that's going to be 50. A is still 0, B is still 600. So we start at 0, go up 50. And we start at 50, go to 100. 100 to 150. 150 to 200. 200 to 250. 250 to 300. 300 to 350. 350 to 400. 400 to 450. 450 to 500. 500 to 550. And then 550 to 600. Brackets on all of these guys. Now, I use the tables to show you how to set things up. I'm not going to require you to do these tables to get full credit, but just know that you are going to have to look at each of these intervals. And again, we started at A, 600 is B. So we know we've hit all, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have our 12 intervals. We go from A to B. We're all okay. So now we look at our values. So x sub I for 0 to 500, x sub I is 50. And in fact, you may have noticed a pattern, or I'm sorry, that's not 50, it's 0. It's the first number in your interval, and that's what your x sub I is. So this is 0, 50, 100, 150, 200, 250, 300, 350, 400, 450, 500, 550. Extend these a little bit. And then it's just plugging in these values back into our function, way up here, 600x minus x squared. So f of x is 600x minus x squared. And plugging these in, f of 0, 0, f of 50 is 27,500. Now, when you're doing multiple iterations on the same problem like we are, notice we already have the values for these numbers. The function hasn't changed, so the answer hasn't changed. So I can go through right now and say, okay, f of 100 is 50,000. I'm not recalculating it. F of 200 was 80,000. F of 300 was 90,000. F of 400 was 80,000. And f of 500 was 50,000. So we don't have to reinvent the wheel here. We're not recalculating everything. We're just doing about half the ones that we don't know. So we would have to plug in 150 into our function. And when you plug in 150, that's 67,500. Plugging in 250, that's 87,500. Plugging in 350 is 87,500 again. 450 is 67,500. And 550 is 27,500. Now I do have to give a little disclaimer here. I've chose this function specifically because it mirrors its values to make our life a little bit easier. But not every function is going to do this. Some quadratics will look like this, but not every quadratic will. And so our values here, again, we can't reuse these values anymore because our delta x has changed. So we do have to multiply 50 times all of these numbers. So just going down the line, 0 times 50 is 0. 27,500 times 50 is 1,375,000. 50,000 times 50 is 2.5 million, or 2,500,000. This is going to be 3,375,000. The next one is going to be 4 million. The next one after 4 million is 4,395,000. At the 300 mark, 90,000 times 50 is 4.5 million, or 4,500,000. And the nice thing is these values now repeat these, but in descending order. So we've already done 87,500, 4,395,000. We've already done 80, it's 4 million. Then it's 3,375,000. Then it's 2,500,000. And then it's 1,375,000. And then again, it's just one big addition problem. You just add all these up, obviously in a calculator, big numbers. And we get 35,750,000 as our approximate area. And this is going to be more accurate. Than part A. It's more work, for sure. 12 intervals, 6 intervals. But it's also more accurate. Because we can just look at the rectangles from part A versus the rectangles in part B. So the first rectangle from A starts here, counts this, then this, then this, all the way down, then this, and then this. So we can see the difference. We have less excess here and here and here in these three rectangles. There's more blank space that we're not counting. And over here, we filled in more of what was missing from this one. And so we know that, like we said in the previous page, we're missing less over here, and we're counting less of the extra that we did over here. And so this was 12. We could go to 24 rectangles and be even more exact, split all of these 12 rectangles in half, and we'd be even more accurate. Now, that's a lot of work. It's 24 rectangles. So, on this next one, I want you to try this on your own. You know how to construct it. You know how to set up the intervals. I've even given you the diagram, so your delta x should match properly. Set up your table and see what your area comes to. Right? And you can always check your work because I already gave you the rectangles. But we want to get going on how to make Riemann sums a little bit easier. So as we said at the beginning of the chapter, it's not always necessary to use a Riemann sum. And we want to identify a couple times that it's not necessary. So the first time is the constant function, f of x equals b. So these are cases where we don't use Riemann sums. For these two cases. The first is the constant, f of x equals b. We don't want to use this because we know this is the point x comma b, and this is x. The area equals base times height. This is x times b, or just xb. So if you have a constant function and you're finding the area under it, don't use Riemann sums. You're just adding work. We're just going to use the fact that we know that that's going to be a rectangle. Same thing for y equals mx plus b. This point here would be the point x comma y. This is a triangle. All linear functions are triangles. We don't need to use a Riemann sum. We can get the exact area. Area is 1/2 base times height. The base is x. The height is y. Because that would be the y point right there. And our y, we know, is mx plus b. So this is 1/2 x times mx plus b. So when you have a constant function or a linear function, do not use Riemann sums. It will only make you do more work and make you more frustrated. We have known area formulas that we can use. So let's take a look at last little example here, and then we'll introduce the big topic for the next section and call it a video. So we're going to consider the function f of x equals 5, and we want the area under that curve. Well, and here we're being a little bit more specific. We don't just want the area, we want an area function, a of x. So a of x, whatever this x is, right? So this is just a general x down here. This is 5, which is the height, times x. So a lot of times when we have these known area formulas, we find area functions. Well, 5x is our area function. So then a of 1 equals 5 times 1. That would be this rectangle. That's just 5. A of 2 would be this rectangle. That's just 2 times 5, or 5 times 2, which is 10. And a of 7 would be way out here, would be this whole thing. This is just 5 times 7, or 35. So if we have a nice known area formula for constant functions or for linear functions, we can construct an area function, and we don't have to just know the x, the one specific thing, because the area is not going to change. Base times height, no matter what x is. The height's always 5. So the next couple sections are all devoted to definite integrals, so we want to introduce that here. And so that's what we've been developing with Riemann sums using these subintervals. As we talked about, the more subintervals you have, the more accurate your approximation of your area becomes. As we increase the number of intervals, the width of our rectangles gets smaller. Or in other words, delta x gets small. So now we want to connect this back to what we started the class with, the semester with, that is. If n is allowed to approach infinity, then delta x gets even smaller, and this is important here, delta x approaches 0. Well, that's nothing more than a limit to our approximation. And if we allow infinite rectangles, then we will have the perfect area. So that's what gives us our definition of definite integrals. So if y equals f of x is a continuous, non-negative function over a closed interval a to b, then the area under the graph of f of x is given by the infinite Riemann sum the sum from I equals 1 to infinity of f of x sub I times delta x. But delta x, which equals b minus a over n, if n is now infinity, this goes to 0. Remember, we've said as the denominator in the fraction gets really small, the fraction, or really big, the fraction gets super tiny, going towards 0. So we don't want to think of it this way. We want to think of it as a equals the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I times delta x. Well, as the delta x, as n goes to infinity, we have an infinitesimally small change in x, and we know that as the differential of x. That's the whole idea behind derivatives, is the dx, the d dx, is when we take the change in x to 0, which is essentially what we're doing here. Delta x is going towards 0. And delta x approaches 0. Well, that means that this becomes a dx. And as it turns out, when we take the limit of the summation, this whole piece here becomes the integral of f of x. Our delta x becomes dx. And the way that we account for the b and the a is we have a to b. And this is a definite integral. Definite integral. And this gives the exact area under f of x from a to b. And here's the best part, is our integration, all of our rules from 4.1 don't change. So in this example, we're not going to do the geometric, we're just going to do algebraic. So we are integrating from 0 to 2, 3x plus 2 dx. So when you have a definite integral, we kind of ignore the bounds. So these are called the limits of integration, the a and the b here. we ignore them until the very end. So pretend that these aren't here. We're back to 4.1, finding antiderivatives. And this is power rule on 3x is 3x squared over 2. Power rule on 2 is 2x. Now here's where it changes. So once you have the antiderivative without the constant of integration, we put this in parentheses with no constant, and we have 0 to 2 with this bar. Now this bar says you're going to take this function and you're going to evaluate it at 0 and you're going to evaluate it at 2. Or evaluate from 0 to 2. So when you have a definite integral, you replace the constant of integration, the unknown constant, with the known constants, because we know what those are. And to evaluate this, the way that this looks, you first plug in 2. So you have 3 times 2 squared over 2 plus 2 times 2. That goes in its own set of brackets or parentheses, and then you subtract what happens when you plug in 0. 3 times 0 squared over 2 plus 2 times 0. So this is how we evaluate. That's what this symbol means. It means plug in 2 and plug in 0 and subtract the bottom one from the top one. And by bottom, I mean the bottom number plugged in and the top number plugged in. So this is just 3 times 4 over 2 plus 4 minus 0 plus 0, or 6 plus 4, which equals 10. And since this is a unit, this is an area, we have units squared since we don't have a unit. So that's how you evaluate that definite integral. Now, the next couple sections are all going to be about evaluating definite integrals. So don't feel like you need to understand this perfectly here. But this is the end of 4.2. In 4.3, we'll be talking about definite integrals a whole lot more.